Good morning. Thank you, Peram. Good afternoon and good evening to the participants in Europe and Asia. Uh, I'd like to start by also introducing my colleague, Aaron Pahala. He is our VP of Innovation, and I'm delighted that he can join us during this tech talk. Aaron's been in the rubber industry for over 2 decades. More importantly, he spent 10 years with Goodyear, and he's also the inventor of SureMix. So as we go through the presentation, I'll call on Aaron to help me through the conversation. Okay, so let's start with the presentation. So I've divided the presentation to the following sections: a brief introduction to Polymer Solutions Group, uh, understanding our approach to the rubber and tire industry. Uh, why did we as a company focus on different areas that we believe are of value to the industry? Next, we'll move on to understanding SureMix, and then applications which are related to sustainability. So how do we correlate actual performance and processing benefits into sustainability targets that the rubber and tire industry is focusing on? Then we'll have a question and answer session, and there's an appendix with a lot of information. When we've given similar presentations, customers have asked us for additional information on the references we used or more details on the formulations. So we've put that in the appendix. You can reach out to Peram. I'm sure you have his email, and he can provide you with a copy of the presentation. So let's start with an introduction to Polymer Solutions Group. So who are we and what do we do? Polymer Solutions Group started at the end of 2015, and we'll show you which are the companies that make up Polymer Solutions Group. But it's more important to understand where we focus. So we have different areas of focus around the rubber and plastics industry. The rubber additives, that's the business unit I manage. Rubber chemical dispersions, where we convert chemicals, whether it's liquids, powders, solids, into a more easy to handle, manage, safer form. Then anti-tack and release agents. In North America, I think right now we are the leading anti-tack solution provider. Our approach has been very different from the rest of the industry. That's what's given us a leadership position. Aaron's group also works in advanced chemistry. SureMix is a product that came out of his team in 2015. We have a growing line of plastic additives where we've adapted or expanded our base technology for plastics. And then we are now expanding rapidly our release agent technology into engineered wood applications. So as you can see, quite a comprehensive portfolio of different products. We don't make any end product. We just make materials work and perform better. So when you think of Polymer Solutions Group, as I was talking to Peram last week, we have to do a little bit of work on our brand identity. Many people haven't heard of us because we're just 5 years young. But the key companies that make up Polymer Solutions Group are Flow Polymers, based in Ohio, Sasco, based in Albany, Georgia, and Alcon Solutions, which is based in Milan, Italy. Those brands, Flow, Sasco, and Alcon, are pretty well recognized in the industry they serve. And at present, we are in 50 countries. I would say 18 of the top 20 tire companies are either commercially buying from us or in the process of approving our products. And nearly, I'd say about 5 out of the top 10 rubber companies are our customers. So a very broad footprint out of North America, and we're delighted that we have a global audience for this presentation as well. Here's a brief history of Polymer Solutions Group. This was a group created by a private equity company called Arsenal. They then acquired Flow Polymers. Aaron and I were part of Flow Polymers, and we're part of Polymer Solutions Group now. And with the support of Arsenal, we kept growing the business by acquiring Sasco, Alcon, and then expanded into Wood Release with the acquisition of divisions from Michelman and Pure Polymerics. And in 2019, at the end of the year, just prior to the start of COVID, we were acquired by the Jordan Company. The Jordan Company is another private equity company. We really like this firm because it is operationally focused and they've been supportive of our expansions through the years. So that's the makeup of our company. So what are our products or our product lines? For additives, we basically have three product lines. ProMix, which is, I'd say, used in nearly 40% of the tires worldwide. It's a homogenizing agent that is added to the inner liner to help improve processing and performance of the inner liner. In addition to that, we've seen good growth outside the tire inner liner to different tire components. SureFlow is a product made with patented technology for plastics, especially for highly loaded polyamides or PET type plastics. So these were our mainstay products made in Cleveland. And then in 2018, we started building a new line for a new class of process aids. We call them functional process aids. And as we go through the presentation, I will keep emphasizing the word functional so you understand that this is a different type of material and precisely why Aaron and his team were able to patent the technology and the applications. SureMix is also 100% bio-based carbon, and that's why it helps rubber and tire companies meet their sustainability objectives. As we talk about sustainability, I want you to keep one thing in mind. It's also performance and profitability. Unlike many companies, we're not just focusing on one area, and I'll talk about that a little later. We're taking a more holistic approach to the rubber industry. The other two divisions, the rubber chemical dispersions and release agents, we've got a few product lines for those as well. Fluorospurs is a well-established product line, mainly distributed in North America. Similarly, our anti-tack coatings, the Polycoat, Sascoat, and Alcon, I would say are in the Americas and Europe, and we're slowly expanding further east into Asia. And our engineered wood, which is release agents and fire retardants. It's a new line we've got quite a few new lines of products, again, mainly North America focused. So I'd used the word holistic a few short while ago. So let's understand what do we mean by holistic. When we look at the rubber and tire industry, we're not focused just on one aspect. Either you're sourcing a green material, or you're producing a part with lower cost, or you're trying to optimize performance, or you're focusing on the mobility, the wet traction, the rolling resistance of the tire. Our product, or SureMix product line, is designed to impact all the 5 areas that I've mentioned over here: sourcing, manufacturing, performance, profitability, and mobility. And it's also very well aligned with the sustainability and performance goals and aspirations of our customers. This presentation actually came out of our approach to the market. We would talk about sustainability with technical teams, and this is before the tire industry project, where many people have started getting more and more focused and started sustainability group divisions within the organization. Our customers would mention, do you have a product that meets sustainability requirements? How much does it cost? How does it perform? And we've helped the industry understand how this product can help them achieve their goals. There's a lot of information in this presentation, so we've broken it down into 3 sections. Sourcing, and we'll talk about, and each section will end with a slide based on the topics over here: sustainable sourcing, responsible operations, and advanced mobility and safety. So our goal over here is to link performance and materials to the topics we've presented over here. Aaron, is there anything you would like to add at this point?
No, Ricky, no, I can speak a little bit to what you have on the slide right now.
Sure.
SureMix, Ricky mentioned that our team developed SureMix with a focus on both sustainability and improving processing and performance in tires. So it's important to understand that SureMix is derived fully, all the carbon in SureMix is derived from bio-based sources. That is something that we've adopted as a driver for us as we develop new products. Our manufacturing process for making SureMix is actually a very responsible process. Our temperatures are quite moderate. We have no organic solvents used in our process, and the only reaction byproduct in our manufacturing for these products is water.
Thank you. So let's move on to understanding SureMix. It's a real challenge when you bring something new to a well-established industry. I remember back in '93, I was working in oil and gas, and I got a call from a carbon black company and said, "Would you like to join us to make a silica-like carbon black?" And I go, "Why?" They said, "There's a patent out from Michelin, and we are really worried that in 2 to 5 years, nobody will need carbon black. This stuff is amazing." Well, we're sitting here in 2022, and as you all well know, silica is growing, but there's still a lot of carbon black used. The point is, it takes a lot of time to drive change. What we're trying to do is shorten that cycle by helping people understand what our product is and how it's positioned in the market. So let's talk about the product. It's a functional process aid. So the best analogy I can give you is if you think of solution SPR and functional solution SPR, there is a functionality added to the polymer so that it can improve performance. That's the think of SureMix with the same analogy. There are a lot of process aids there. When you add a process aid, you get good processing, but your performance falls apart. Many of our customers, when we spoke to them and say, "Have you tried a conventional process aid?" And they would say no. Either the cure changes or the modulus changes or hysteresis goes up. So we developed a product. I don't know how many iterations, Aaron, but there must have been dozens that you tried before S6 was.
Yeah, many dozens of iterations.
Many
and really many dozens. And we really have utilized chemistry that's not being used today in the industry, outside of SureMix. And that's something we can certainly get in more deep with anybody who wants to follow up with us, after this presentation. The chemistry is very exciting, and we can show you how it works.
So what we've been saying for, I think, 5 years now, thank you, Aaron, is you can formulate without compromise. So if you take a rubber roller, we were working with a company that makes rice dehusking rollers. And they said, we need better processing because our compound is very stiff, because we need a hard roller, but we can't use a process aid. So we said, okay, try SureMix. And lo and behold, they can process it. the roller lasts longer. There's less broken husk, uh, fewer broken rice grains. So, at the end of the day, we have helped customers, whether you're tire or non-tire, compound without the conventional compromise, whether it is in performance, whether it is in processing, or it could even be in the cost of the product. We can come up with a better solution just using SureMix. Uh, it was introduced for the tire industry, so we have focused on areas like tread life. You can look outside the tires and consider any rolling component. If it's a roller or a conveyor belt, you can increase the life. We also, by optimizing the mixing process, and we'll share some data with you where we've taken 2 or more mixing passes out of a mixing cycle, we can help reduce the cost. It's not just the cost of mixing, it could be substituting materials, which helps reduce cost, improved extrusion rates, which helps reduce cost. We helped a natural gas hose manufacturer reduces mill time from, uh, I would say, 20 minutes down to 2 minutes. They had a tilt mixer which dropped on the mill. So there are many ways where processability improvements impacts the cost. And as Aaron emphasized a little earlier above, this helps. We also have a biocarbon base which helps our customers achieve their sustainability goals. So let's move on and really see how SureMix works in rubber. So this is a simple, this is a section of a formulation, and the full detailed formulation is in the appendix, but we only wanted to focus on a couple of things over here. One is our customers want to increase silica loading. This is one of the, I would say, most important trends in the tire industry. Increasing silica increases wet traction, and as people are looking at autonomous cars, looking at battery electric vehicles, increased silica also helps increase the tread life of the tire. But there are problems. It's difficult to mix 100 or 120 or 140 pHr of silica. The viscosity of the compound increases significantly. There's also a performance penalty. As you increase silica, you also increase hysteresis. So how do we address that? So we took the formulation which had 100 pHr of silica and added 5 pHr of SureMix. And on the next slides, Aaron will walk you through the property changes on the processing side and then on the performance of the compound. Aaron, over to you.
Thank you, Ricky. Right, so you can see in this compound, right? So increasing the silica loading from 80 to 100 parts. For those who've either done that or tried to do it, one thing that you'll know is that it's very difficult from a processing standpoint, but the performance gain is incredible. So going from 80 to 100 parts of silica, the wet traction improvement is very substantial. So this is something that everybody would like to be able to do in a tire tread, but it's extremely difficult in a manufacturing environment. So you can see if you look at uncured G prime, and we use uncured G prime on RPA, we usually talk in those terms as opposed to Mooney viscosity, simply because the RPA is very sensitive and we can see changes that sometimes won't show up on Mooney viscosity alone. But you can see the increase in the uncured G prime, increase in the viscosity going from 80 to 100 parts of silica in the black to the red bars on the top left here. So it's a 45% increase in the viscosity of the compound. Using SureMix in that 100 part compound, we're able to reduce that viscosity by 40%, bringing it down very close to the viscosity of the 80 part silica compound. Also important is the stability of that viscosity. So if you've mixed silica, you'll know that And the viscosity when you mix it is just part of the challenge. So after you mix it, as that compound sits around, you get flocculation of the silica, which drives the viscosity up further. You see the 100 part silica compound goes from 290 to over 300 on the uncured G prime, and is essentially unprocessable at that point. And you can see that reflected in the Garvey extrusion below. Those are the Garvey extrusion pictures from our laboratory. Going from 72 to 95 with the extra silica, you just get to the point where the compound is unprocessable. However, if you use SureMix in that compound with 100 parts of silica, you see that dramatic drop in viscosity, and you see the smooth extrusion, right? And at that point, you have a 76 Mooney after 7 days, very close to the 72 Mooney of the 80 part silica compound. So one thing that we always like to point out is also the uncured tangent delta. Uncured tangent delta, if you're not familiar with it, is a great tool to show you the processability of the compound with respect to how smooth the compound is going to extrude. All right, so the uncured G prime gives you viscosity, the tangent delta gives you smoothness of extrusion. And in this case, higher is better. And you see the improvement going from the red compound to the green by the inclusion of SureMix. Okay, so another challenge when you're going from 80 to 100 parts of silica or even higher, as Ricky mentioned, is that there's often an effect on the cure. Right, the more silica you have in the compound, the more absorption of accelerators you're going to get to the silica surface. So you see going from the black to the red curve, you see a couple things. You see the flocculation of the silica early on, which causes the increase in the viscosity and the earlier increase in the viscosity. And then you also see the marching modulus of the compound. So you see the red curve continues, instead of being a plateau, it continues to rise. So that can be caused by the accelerators being absorbed to the silica surface and then over the course of the cure being released from the silica surface. When you use SureMix, what you can see in the green curve, you see the type of step that you like to see with a sulfenamide cure. You see a low viscosity, a fast increase, and then a plateau. And this happens because SureMix actually has a higher affinity for the silica surface than the accelerators do. So SureMix is able to outcompete this for the silica surface and keeps the accelerators in the rubber, in the compound bulk, cross-linking the compound. If you look on the right-hand side, you see the pain effect. So again, great use of RPA. We measure the uncured pain effect. And you see here, if you're familiar with pain effect, flatter curve is better, right? So if you see going from the black curve to the red curve, you see that the slope increases, right? So that means that you have poorer dispersion of the silica. So by putting in that extra 20 parts of silica, it becomes very difficult to get it dispersed, and you see that increase in the pain effect. By using SureMix in this compound, we're able to decrease the pain effect and flatten the curve. So you see the green curve is down flattened close to the black curve, and that's with 20 additional parts of silica. So incredible improvement in silica dispersion using SureMix. So SureMix drives silica microdispersion, and you see that reflected in the properties. If you look at the tensile properties here on the left, you see going from 80 to 100 parts of silica, the black curve to the red curve. You see the increase in the modulus, which you would expect from the higher level of silica. But then you see a drop in the tensile strength and a drop in the elongation. Now that's a result of not being able to get the level of dispersion, microdispersion on the silica that's needed to maintain the physical properties. By using SureMix in this compound, we're able to improve the elongation and improve the tensile to get to the level of tensile that's expected by having the dispersion, the degree of dispersion in the 100 part silica compound that we had in 80. And of course, here on the right, the main thing that everybody looks at, right? What is the hysteresis? When you're talking about silica dispersion, the expectation is a reduction in hysteresis. Here you see going from the black curve to the red curve, you see that increase in hysteresis that Ricky mentioned. That comes from the challenge of getting the dispersion of that extra silica. Using SureMix in this compound, we're able to take the hysteresis down from the red curve to the green curve. So here we have hysteresis very similar to the 80-part compound. So in the end, you have a compound with 100 parts of silica with tremendous wet traction and very little hysteresis penalty. So you have the fuel economy of the 80-part silica compound with the wet traction of 100 parts of silica and incredible processing in the plant.
Thank you, Aaron.
Sure thing, Ricky.
So to summarize this section, I'll go back to one of the statements we've made is formulate without compromise. The whole goal of the study was to increase silica to improve wet traction without compromising processability and performance. And we have some applications where the silica loading is so high, when we ask the customer, where is your control tire data? They tell us we can't make a controlled tire without SureMix. So where the industry has reached today is at the point where you can't mix without a functional material that can help you achieve the processing requirements. So we'll close out this section again by reiterating that we are very responsible in our sourcing and in our manufacturing. We have two commercial grades right now, S6 and CO squared. They both designed to function slightly differently. S6 is more used in carbon black applications and CO squared more in silica, but they can be used together. So if we look at the EPA Green program, we have applied 8 of the 12 green principles in manufacturing SureMix. The other 4 don't apply to the type of product we make. Some of the key ones, as we had mentioned earlier, it's a low temperature process. We do not use solvents, and we have water as a byproduct. So we're not disposing of hazardous materials. So now we'll move on to another section which will focus on another aspect of performance and sustainability. And we'll look at 2 examples over here. I'll cover the mixing cycle optimization, and Aaron will cover the VOC reduction. And at the end of the section, we'll help you estimate what is the impact on greenhouse gases. So this was quite a challenging study for us. The data that you see out here, of course, is lab data, but it's been validated in factory environment. Tires have been built and tested. We've been able to meet the performance and processability requirements. So the customer was using a N234 or N200 series, a carbon black, and switched to an N134 to improve tread wear. Unfortunately, by doing so, they went from 4 to 5 passes. So the goal was to get them back to a 4-pass mix without compromising any of the properties such as modulus, tan delta, J double prime. This is a truck tire application. You must have guessed looking at the natural rubber and butadiene ratio as well as the type of carbon black used. So what we did is we mixed in a 4-pass as is, no change to the formulations, and then we looked at 3 different levels of SureMix and saying, okay, what would be the ideal level for this application where we can meet the performance and the processability requirements? So as you can see over here, everybody looks at Mooney, which is fine. You can see an increase in Mooney as one pass is taken out, as you go from 5 to 4 pass. And the when SureMix is added, you can see again a drop in Mooney. These are all 4-pass mixes. We prefer to look at G prime, and G prime is more sensitive. And over here, it's important to note that while we saw 69 Mooney for the 5-pass control and 4 PHR SureMix, we see a lower G prime 221 versus 207. But if you look at the 6 PHR, we've gone from 221 to 188, or you can say from 229, and a reduction of 18% to 188 kilopascals. So a significant reduction in G prime. So our work in the lab was to, and then further in the plant, was to focus on the 4 PHR mix, take baby steps rather than a leap of faith, and try to save as much mixing time as you can. We do have customers who have taken 2 mixing passes out in some silica compounds, taking full advantage of the viscosity reduction of SureMix. But even if we look at the Mooney, we can see with the 6 PHR, we could very easily take 2 mixing passes out. But even 1 mixing pass out is a throughput increase of 20%. Secondly, with the lower G prime, we know downstream processing is much improved. We won't have time to cover it in this, but what the customer did see, in addition to the lower viscosity, there was an increase in stiffness or modulus of the tire lugs. And we have now figured out why. SureMix actually prevents reversion. So since this is a natural rubber formulation, the tire tread does not revert. We are able to maintain a higher modulus, which is beneficial. So let's look at the physical properties. So in this case, up to 4 PHR, we saw no change in the tensile curves. The tensile strength and the elongation to break, and especially the modulus, remained unchanged. We also looked at the dynamic properties, E prime and E double prime, and we found no change in those. So in other words, the properties were unaffected, but the processability was significantly improved, allowing the customer to eliminate 1 mixing pass. We'll now move on to a very novel concept that Aaron and his team came up with. So I'll let him cover that. Please go ahead, Aaron.
Thank you, Ricky. So this is what we call high performance salinization, and let me give you a little bit of background before I jump into the data. So when you think about use of silane in a silica compound, in a silica tread, the majority of the work that was done to establish silane loadings was done obviously many years ago, and was done using Si69 type silane, so tetrasulfide type silane, and it was done within the bounds of processability. So what you'll see is a typical recommendation of 8 parts of silane per 100 parts of silica, and that was based on what properties could be developed during mixing within a mixed cycle where you could get compound that was processable, right? So that was kind of the box that was being worked inside of. So what we looked at as we were considering the dramatic processability improvements that we get with SureMix, we thought, was there an opportunity for 2 things? One, was there an opportunity to do salinization in the mixer at a higher temperature using SureMix? Basically buying a processing window at a higher temperature because of the improved processing with SureMix. So we would want to do that because by going to a higher temperature, you can drive the salinization reaction. And in doing so, you can get better silica dispersion and a further reduction in hysteresis and improved fuel economy. And so then the other thought we had was, well, if we can do that, if we can go to a higher temperature with silica and salinization using SureMix CO squared, does that give us the opportunity to reduce the amount of silane in the compound? So if you think about it, you know, it's a typical reaction, right? If you're able to drive it further by going to a higher temperature, then you may not need as much of one of the reagents because you can get a higher degree of reaction. So that's exactly what we tested here, which led to the concept of what we call high performance salinization. So in this formula, you see we have a silica tread solution SBR, polybutadiene with 100 parts of HD silica and TESPT, so Si69 type silane. And we did salinization in a control compound at 150 degrees C, and then in a test compound at 170 degrees C. So if you're familiar with the processing of Si69 in silica treads, 170 degrees C is something you would typically not do because the processing is not going to be so great, because you get liberation of sulfur and you get cross-linking in the mixer, and your processing goes bad quickly. So we also have a compound at 170 degrees C salinization temperature using SureMix CO squared. And then the final one here is 170 degrees C salinization with SureMix CO squared, but with a reduction of the silane by 37%, 38% in fact. So one thing that you'll also notice is the sulfur loading. So whenever you decrease, or actually whenever you change your silane in your compound, in a sulfur cured compound, it's important to adjust the total sulfur in the compound so you can maintain the modulus, because by taking out silane, we're taking out the donating sulfur from that silane. Now, important thing to realize is that as we reduce the silane, right, so by it being enabled to reduce the silane with SureMix, we have a reduction in the ethanol liberated during mixing. So you may say that ethanol is just burned in our oxidizer if you have one equipped on your Banbury, but every time you burn the ethanol that's liberated, you're generating more CO2 in the environment. And there is also some left in tires liberated during use as well. So you see the reduction of almost 400 kilograms per 100 metric tons of compound with the reduction in silane that we're talking about for this formula. Okay, if we look at the processability of these compounds, again, we're looking at RPA, uncured processing. You see the increase in the viscosity going from 150 to 170 degrees C, from the black curve to the red, from the black bar to the red bar, and you see the decrease in the viscosity using SureMix CO squared. In the green bar at 170 degrees C, and then with the reduction in the silane, you also see that nice low viscosity. So in both cases, using SureMix CO squared, whether it's at the control level of silane or at the reduced level, you see a viscosity that's lower than the control compound, even though we're processing and performing salinization at 20 degrees higher temperature. And you also see the drop in the uncured tangent delta going from 150 to 170, and what that tells you is it's going to be a rougher extrusion, which you see below. And then you see the increase in the uncured tangent delta as we add SureMix and reduce the silane. Now the garbage dye extrusions in this case show a lot. Going from 150 to 170 degrees C, you see the compound roughness. You see those numbers above, those are actually the Mooney viscosities. So in the case of the 170 degrees C compound, 82 was the compound viscosity as mixed, and an increase to 103 after 7 days storage at room temperature. The compounds containing SureMix maintain viscosities down in the 70s, very close to the 150 degrees C salinization control. So here we're able to utilize SureMix CO squared to get 20 more degrees of salinization temperature, which is going to drive the dispersion of the silica dramatically to improve the properties. And we're still able to process it. So let's take a look at the properties.
Just before we go across, I just wanted to point one thing out. The
Sure.
If you look at the Mooney viscosity after 7 days for the one with high performance salinization, it's at the same Mooney viscosity of the 150-degree control as mixed. This is also a challenge for a lot of silica compounds, which require remilling if you store the compound before you can extrude it. It doesn't matter what the application is. The higher the silica loading,
Great
the
point.
more the requirement. But when you add SureMix, even after a week, the processability is not compromised.
Great point, Ricky. Thank you.
Thank you. So we'll move on to the properties.
Okay, so using the higher temperature salinization, right? So I mentioned that what happens is you're going to drive the reaction, right? You're going to drive and improve the dispersion of the silica. But in the case of the control compound, you see going from the black to the red on the left. If you look at the tensile, you see an increase in the modulus for all of the compounds at the higher temperature. And that's due to the liberation of the sulfur from the tetrasulfide due to the higher temperature. But for the control, you see a big drop in the tensile and elongation. So what's happened there is you've gotten pre-scorch, some pre-cross-linking in the mixer during processing. And what you, as a lot of you know, if you continue to mix, while your compound's starting to cross-link and pre-scorch, you're going to tear the polymer, reduce the molecular weight, and you're going to lose properties, lose ultimate properties. You see the two compounds with SureMix CO squared, the green and the yellow curves. We're able to protect the compound during the higher temperature and get a very good tensile and very good elongation development. Of course, the whole goal of going to the higher temperature was to drive the salinization reaction and to improve the hysteresis and fuel economy of the compound. So you see going from the black curve to the red curve on the right, so the hysteresis by DMA, you see that reduction in the hysteresis. So if you could go from the black curve to the red curve, right? If you could do that in production, if you could mix that compound, you would do it because that's going to be a benefit in your tire. You're going to see improvement in fuel economy in those tires. The problem is in that red curve, you just can't mix it. It just can't be done. Processing is way too difficult. Using SureMix CO squared, we've shown that we're able to process it, which we've shown we're able to maintain the tensile strength. But here you see the dramatic reduction in the hysteresis. So as much as 27% reduction, and you'll notice that even with the reduction in the silane, we get a dramatic reduction in the hysteresis. And in fact, it's a little bit lower than the compound without the reduction in the silane. So what this shows you is that dramatic reduction in the hysteresis shows you how powerful SureMix is for hydrophobating the silica and achieving the silica dispersion to get that low hysteresis result.
Thanks, Aaron.
Sure thing, Rick.
So to reiterate this section, our goal over here was to set the new benchmark on rolling resistance. And you can see that was achieved just by making slight formulation adjustments, the addition of SureMix, and optimizing the mixing cycle. So the previous example was on mix cycle reduction. This was on ethanol reduction. So how do these affect your sustainability goals? So let's look at mixing and processing efficiency. The feedback that we have at the factory scale is a 20 to 50% reduction in energy consumption in the internal mixer. That is driven by two factors. One is fewer mix cycles, especially highly loaded silica compounds have to be milled multiple times to get the viscosity in an acceptable range and get the micro dispersion to an acceptable level. With SureMix, you can have a dramatic reduction. The second is the lower viscosity. If you may recollect, we showed you the G prime. Even though the compound had a Mooney of 69, the G prime was for the control 5 pas and the SureMix 4 pas. The viscosity was lower when you measure it by the G prime. And this is seen by the torque requirements of the extruders and other production equipment. So let's take a conservative approach and say, okay, What happens if we only reduce our total energy consumption by 20%? What does that mean? So in a mixer, we pulled this information from HF and the EPA. Again, these references are in the appendix. The mixer is a 320 liter DC motor drive, 18,000 metric tons a year throughput. Energy consumption is 2.6 K megawatt hours. So if you have a 20% reduction in energy or a 20% increase in throughput, uh, both of them will lead to reduced greenhouse gases or carbon dioxide per metric ton of compound. So assuming uh, we mix it with one less pass or 20% less, 20% of 2.6, so 2600 is 520 megawatt hours of energy saved. Each megawatt hour of energy is about 453 kilograms of carbon dioxide. So for a 320 liter mixer, saving 20% of the energy is saving 235 metric tons of carbon dioxide emissions. So if you think about it, larger mixers or multiple mixers, the impact of reducing mix time or mixing passes is dramatic on your carbon footprint. Uh, Now moving on to ethanol, yes, there are scrubbers, but uh, again, as Aaron had said, those lead to further greenhouse gas emissions. But there are also a lot of operations that don't have scrubbers. And there are, even in the case of scrubbers, there are fugitive emissions. So we have worked with customers where the silane can be reduced by 25 to 38%, and that is an elimination of 220 to 380 kilograms of ethanol. Everybody's familiar with the greenhouse warming, global warming impact of greenhouse gases, mainly carbon dioxide. But alcohols like methanol and ethanol are 1,000 times worse. So every kilogram you save out here is a significant impact on the carbon footprint of your operation. So what we've covered, I would say so far, is the state of the art where we are today, but we'd also spoken about future aspirations and setting the benchmark. So let's look at what SureMix can do to help you further down the line, especially from a performance standpoint. If you're familiar with the new generation of tire compounds, uh, the industry is moving from solution SPR to functional solution SPR or blends of those. So in this study, what we wanted to do was to compare uh, what are the benefits from moving from a solution SPR to a functionalized version of the same polymer. So we took two polymers, Printan SLR 4630 and 4633, which had very, very similar microstructure. The main difference is one has functionality and the other doesn't. We also looked at the impact of SureMix in these formulations. So we took our solution SPR control and added 6 parts of SureMix. Here again, we have 100 PHR of HD silica and the recommended 8 PHR or 8 PHF parts per 100 of the filler of tetrasulfide silane or Si69. Similar approach on the functional polymers, 100 parts of silica, 8 of silane, and then added 6 PHR of SureMix CO squared. So let's look at the Mooney viscosity to start with. If we take our true control for the study, which is the black line, that had a Mooney viscosity of 85. As expected, when you add SureMix, the viscosity falls to 73. If any of you have mixed functional polymers, you know one of the big challenges with these polymers is the increase in Mooney viscosity or G prime. So it increases from 314 to 331. Adding SureMix again drops it down to 265. What is really interesting to me is if I look at the Mooney viscosity of the functional polymer with SureMix, it's lower than the control. In other words, it should mix and process better than the control without SureMix, uh, which is quite unusual when you're using functional polymers. Similarly, if we look at the uncured tan delta, we should see similar performance between the control on extrusion smoothness uh, within the functional polymer. The fact that the viscosity is lower also plays to the benefit of the functional polymer with SureMix. So let's focus on the left. Uh, why are functional polymers used? They're expensive, they're difficult to mix, so why use them? Simply because they help improve tire performance. In this case, if you're measuring hysteresis, going from the black line to the gray line. So the question comes, is there a better way to achieve that same hysteresis reduction? And the answer is yes. If you just take the solution SPR, add SureMix to it, you'll have the lowest viscosity of all the compounds we've looked at in this section, and hysteresis that's even lower than the functional polymer. So you get the best of both worlds. You get the performance targets and the ease of mixing and processing. Furthermore, since the compound has a 6 pHr of SureMix versus 100 of a functional polymer, there's a dramatic reduction in compound cost, as well as compound stability, because functional polymers can have quite an increase in viscosity on storage. But if you want to set a new benchmark, especially for vehicles like electric cars, where charging takes, if not hours, at least 30, 40 minutes to get a full charge. So people want to extend the battery range. In those cases, you want the lowest possible hysteresis achievable. So if you take the functional polymer and you add SureMix to that, there's a further 5% reduction. So all in all, by using the functional polymers with SureMix, we can reduce hysteresis by 14% and increase the fuel economy or the mileage of a battery electric vehicle per charge. Now, there are other things one can do. You'd seen in the previous study that Aaron covered, there was a dramatic increase or decrease in hysteresis with high performance salinization. High performance salinization can also be combined with functional polymers to get another level of performance. So again, we come back to what we've spoken about, formulating without compromise, setting a benchmark without impacting your, or while positively impacting your carbon footprint. So why is fuel economy so important? Well, we'll look at some data on the next page. So if we look at how a 15% reduction in hysteresis can affect the tire's fuel economy. In the case of a passenger car or a light truck, where the tire contributes approximately 4% to 12% of the energy dissipation, by by reducing the hysteresis, that's a fuel economy improvement from half to 2%. When you get to electric vehicles and trucks, the impact is even more uh, significant, because these vehicles have less energy dissipated through engine heat. Most of the energy is dissipated through overcoming air resistance, that's the coefficient of drag, as well as rolling resistance. So any improvement of these in rolling resistance has a larger impact on the fuel economy or the distance a car can travel per charge. If you look at the information published by the EPA, a 1 to 2% increase in fuel economy equates to about 18 million metric tons. So the corporate average fuel economy has a dramatic impact on the greenhouse gases generated. This is just in USA. This is not a global number. Based on the cars on the road, a 1 to 2% fuel economy improvement uh, eliminates 18 million metric tons of carbon dioxide. So just pull everything together. When we're looking at tire manufacturing, the impact of SureMix on tire manufacturing is only on 20% component of the whole cycle of the tire, that is in the manufacturing process. When you look at the hysteresis, you're affecting the 80% greenhouse gas footprint, i.e. the fuel economy or the impact during the life of the tire. So we've gone way beyond just looking at what are the manufacturing benefits, but it's also the benefits in use with lower hysteresis. There are many there are many initiatives out there. One of those uh, currently is what we call the Tire Industry Project, or TIP. In the Tire Industry project, there are two main goals. One is responsible consumption and production, and the other is promote sustained inclusive economic growth. The first one, as you can see, is impacted through uh, the manufacturing, the use of the product. You can impact the eighth goal also, which is another significant one, by helping grow your business through uh, performance, innovation, and differentiation within your market space. And finally, if we were successful today, we hope we were able to demonstrate that sustainability is no longer an option. It is a requirement for the rubber and tire industry. We all are responsible for helping reduce the carbon footprint, and many companies, whether you're automotive or tire or rubber products, are setting goals to be carbon neutral by 2050. We hope with the help of SureMix, we can help you achieve those goals. We also illustrated how uh, sustainability is not mutually exclusive from profitability and performance. This product line can help meet both your profitability and performance targets by reducing the cost to manufacture and set the benchmark on uh, performance, especially things like hysteresis, wet traction, where SureMix is an enabling technology. And finally, we now have an option which will allow our engineers and designers and compounders to formulate without compromise. I'd like to thank especially Peram for giving us this global platform, Aaron for his participation. I was delighted he could join us. I think he had to leave. He had another commitment, but guy's an amazing scientist. So to have him on, I was very pleased. And now we'll open the floor to any questions you may have. And thank you all for participating. I know for some, it's late in the evening. Prior to COVID, I used to spend a lot of time in Asia, and I know how it is trying to meet the schedules of my teams in the US and stay awake late in the evening.
Thank you, Dr. Ricky.